Hi everybody, welcome to another round of seminars. This is the third one, maybe the fourth one we've run now. What I found was that students in grade 12, instead of getting to focus on what they were supposed to be learning, we were going back to units 1 and 2. We're going back to grade 9 and 10 chemistry. Oh, there's Aaron. And well, even my first year university students just didn't have a good grounding in the basics. And I'm sure you've all realized by now that chemistry is effectively just a building block on building block. And if you don't understand the basics, or if they're not taught to you in a way that shows you they're all linked together, biggest gripe with high school chemistry is it's taught separately, and that there's no link between the two, and there's nothing that can explain what's going on. I'm going to do this one. I can do this curriculum mostly out of my head. I'm going to do it on my whiteboard. Anyone that's been tutored by me before knows I'm not the best drawer. And I've been tossing up whether or not to come up with slides or just spitball and go for it on the whiteboard. So if it works for you, not having a slides, let me know. If you want slides, I've got so many resources that I can make something up. That's not a problem. I'll leave it up to you guys. The first thing we're going to go through is the periodic table and the trends. Again, you'll get to see my beautiful drawing. If I do ask questions and you want to answer them, just put it in the chat, because this is being recorded, so preferably not having anyone's face. And I can stop and answer it in the chat once I get to the end of a point, rather than being interrupted. That seems to have worked well. I have 12 different colors, well, 10 different colors now, because I have a 2-year-old. I don't know how long this first session is going to go for, 45 minutes. I'm just trying to get a feel of how much I can fit into one session. What is the periodic table? And I know some of you are probably thinking this is too basic, but I will move through this relatively quickly. So it says the table of elements is all of the elements grouped together with their other elements that are chemically similar. So they're arranged in groups running down the page. Cross arranged into periods. I know there's a couple of uni students, even at second year university level, you're not really worried about the transition metals. So group 1, I'm not going to write group, I'm just going to write 1, 2, otherwise I'll run out of room. So if you look at a periodic table right now, you will see that there are 18 groups. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and then 14. But we're going to talk about trends of the periodic table. Anything group 4 to 13, they are the transition metals. They do not follow the same rules. So instead of changing the rules, we just say that they are exceptions to the rule. So we discount groups 4 to 13, and we count from left, 1, 2, 3. We jump over the big box in the middle, 4, 5, 6, 7, 8. periods running crossways. So 1, there are 7 periods running across. Anyone have any idea of what the groups and the periods actually mean, or what the number stands for? So I also say so a lot. Anyone that hasn't been tutored about me or done one of my seminars, I say so a lot. So Callie has said the periods are the number of electron shells. The groups is the number of valence electrons. Number of valence electrons. We know that the valence electrons are the most important because they're involved in bonding. And to be honest, no one really cares about the other ones. It's not in the outer shell. Don't worry about it in grade 12. Just general chemistry. So number of valence electrons and the periods. So we have sodium, lithium. Now I'm testing myself. Beryllium. Anyone got a periodic table and want to test me? So all of these have 1 electron in their outer shell. And they're all very similar. Sodium and lithium, if you throw a chunk of sodium into water, it will violently explode. So will lithium. Both of them are very toxic heavy metals. Group 8, probably the most boring, but the most important one to understand. So these guys are the noble gases. So group 1 should have said with the alkali metals. Noble gases. So we have neon, xenon, we have helium at the top. Argon. And the important thing to remember here, and I can't stress this enough, is that they have 8 valence electrons, which means they do not react. They are completely full. Hence why they are called noble gases. And we will go through how this fills across in later weeks, not today. Not sure I can deal with doing that today. Oh, see us here. Everybody stare at Josiah. Make it feel awkward. Hi, Josiah. We've just been talking about the periodic table. We've got groups running this way. We have periods running this way. Periods are the number of electron shells. The groups are the number of valence electrons. Over here, we have the noble gases. They are completely unreactive. Group 3, we've got aluminium, carbon, silicon, nitrogen, oxygen and sulfur. We've got fluorine. We have bromine, iodine. When you look at the elements they are grouped as per their chemical properties. They weren't in the beginning, but they are now. So take away from this, the groups going down are the valence electrons. The periods are the number of electron shells. We know in an atom we have the nucleus, which has protons and neutrons. And outside of the nucleus, we have shells that the electrons orbit around. And is that 7? 6. So each of these electron shells, the energy increases the further away from the nucleus they are. The electrons will fill, well, let's do it with hydrogen. So hydrogen, the first electron, hydrogen is element number 1, period 1, group 1. It has 1 valence electron, so 1 electron in its outermost shell. It has 1 going across, so it's only got that 1 shell. We go over to element number 2, helium, and it feels like that. And then it just, I mean, it gets a bit weird after the third, it starts to go backwards, but it will fill heading out that way. And the whole point, or the whole reason that we have chemical reactions happening is to do one thing. And that is to make the elements stable. They have to have, and this is where one of those pesky rules that we always break, hydrogen and helium are completely full when they have 2 electrons. Everything else, to have a full outer shell, it needs to have 8 electrons. And I can explain, just using year 2 maths, why things bond together. So we all know table salt, yummy. Makes food taste better, clogs up the arteries a bit. Nothing too serious. We have sodium and chlorine. Chlorine is also in group 7. I don't know if we get chlorine. Sodium is in group 1. Chlorine is in group 7. They will bond. Something in group 2. No, I can't remember a group 2 element. It's embarrassing. Oh my god, I can't think of a group 2 element now. Anyone give me an element in group 2? Beryllium. So, if something's in group 2, we need to make something go with it to add up to 8. Beryllium and sulfur. 6 plus 2. Okay. I want to make water. Hydrogen is in group 1, oxygen is in group 6. How do I fix that? Two hydrogen. Now, I mean, it's not always that simple, but anything on this left-hand side if you were to look at anything this side, what would the most likely property be? Would it be a metal or a non-metal? Anything group 1, 2, 3, a little bit of 4, 5, and 6, it does sort of cut across like this. So there is some, I mean, it's not always, again, it's not always simple, but I'm going to simplify as much as I can. Over this side, we have metals. Over this side, we have non-metals. Again, for the most part. Anyone ever had a rusty car or, I don't know, seen rust? So rust is caused by metal's tendency to give away electrons. Non-metals like to accept the electrons. What charge do the electrons have on them? Sorry, I was trying to play with the views so you can see that. There we go. Is that better? So, electrons are negatively charged. So if our group 1 element has 1 electron in its outer shell. Now, I'm going to wipe some of this off because it's giving me anxiety trying to write around all this stuff. That's better. I can breathe again now. So if I have my group 1 element, we know that in group 1, it has 1 valence electron. That means to make it all the way over here to having 8 valence electrons, he either has to, or she, sorry, has to lose 1 electron or gain 7. And they don't gain 7. They will always lose 1 to become positively charged. So if I have sodium and I have my chlorine, when they get close to each other, sodium, that's what I assume it happens, says, hey, I need to get rid of 1 of my electrons. Can I give it to you? Chlorine says, yeah, I've got 7, I only need 1 more. If you get rid of 1, you go back to A, and the sodium becomes positively charged, and the chlorine becomes negatively charged. And this electrostatic interaction, like oppositely charged magnets of oppositely charged poles of a magnet, gives us a very, very tightly bound salt. Same thing with group 2. Group 2 element can either give away 6 or, sorry, accept 6 or give away 2. It will always give away 2 to a non-metal. Group 3, exactly the same thing. Can either gain 5 or give away 3. But the idea is that they are trying to get to 8 valence electrons. They can either give it away or accept it. Now, by themselves, the elements are not negatively or positively charged. It's only when they come in contact with another element that is a non-metal, if we're talking about a metal. Group 4 is weird. It can accept or give away 4, depending on what it's bound with. And that's called ionic bonding, this metal and non-metal. Group 5, it's not going to give away 5 electrons. It's going to accept 3 to become -3. So group 1 is +1, +2, +3. Can go either way, plus or -4, -2, and -1. When you're naming a compound, again, this is going back to year 10. When you're naming a compound, the only thing that matters is how do you balance the charge. Sodium chloride, easy, -1, +1. Aluminium and oxygen. So aluminium is +3, oxygen is 2-. Again, simple maths. 3 times 2 is 6. So 2. That gives an overall charge of +6. Okay, I need 3 oxygen. Okay, they're balanced. That would be how you would write aluminium oxide. So ionic bonding is between a metal and a non-metal. And that is when the metal donates its extra valence electrons to the non-metal and they both become full. The metal goes backwards to 8, the non-metal goes forwards to 8. Okay, does that make sense? So I'm going through a lot. There is another kind of bonding. That is, let me get rid of all this, it's stressing me out nonsense. Anyone know what the other kind of bonding is? Ionic and covalent. So, again, we will visit both of these kind of bonds. That's good English. Later on in more depth, but this is just looking at the periodic table. So covalent, they're sharing. Sharing their electrons. We have CH4, which is methane. Now remember that carbon in a covalent bond, again, I'm trying not to go too deep in this because we will revisit it, but it must be surrounded by 8 electrons, 8 valence electrons, and it's high. We know that hydrogen has a single electron. And if you've done Lewis dot structures, you'll remember this. Horrible, horrible stuff. We have carbon, which is in group 4, So it has 4 valence electrons. Hydrogen is in group 1. It has 1 valence electron. So even though if you look at it like, again, it's a beautiful drawing, they're all sharing the outer shell, their electrons outer shell. So that's covalent bonding. Again, we'll go through it in more detail later on. Covalent or sharing between 2 nonmetals. So carbon and hydrogen, hydrogen and oxygen, nitrogen and carbon, nitrogen and hydrogen. Anyone who's done organic chem will know that we have a couple of different types of covalent bonding, but that's for later on. Okay, let's look at the trends on the periodic table. Anyone know what the trends are? I'm just going to pretend this is the periodic table. The big one is the trend of electronegativity. James, very good. Electronegativity. Anyone hazard a guess at what electronegativity means? So, yeah, it's a tendency to take an electron. Now, when we're looking at the covalent bonding, again, we'll go through this in more detail. The most electronegative atom will hog the electrons. So it's not always an even share, but getting ahead of myself. So the electronegativity trend increases this way. It increases that way. Again, we don't bother with the transition metals. They do whatever they want. So, and the noble gases, they don't have electronegativity because they don't react. We use the, and again, you'll see in your exam, you actually get these values. Paulings. So fluorine is 3.98. Francium down here is the lowest. There's virtually no reactivity. Fluorine is the most reactive element. You cannot keep fluorine gas because it will react with anything you put it in and create hydrofluoric acid and eat its way out. You try to put it in glass, you'll come back the next day and you'll just have a puddle of melted glass. So this is really important to understand the electronegativity. It is a determination of the reactivity as well as the tendency for that atom to hog an electron. The other one is ionization energy. Sorry. Ionization energy is the energy required to remove an electron from a neutral atom that's in its gas phase. It is the opposite of electronegativity. So the lower the ionization energy, the more likely it is to lose or gain an electron. So a little bit of terminology. We have cation, which is positively charged because cats are positive. It becomes a positively charged molecule, or it loses an electron. Anions, because onions make you cry. It becomes negative, or it gains an electron. So same thing with almost the same trend as electronegativity. Not that way, but it's the opposite. Electron affinity is how likely is that element in its gaseous phase, how likely is it to accept an electron? Again, follows the same pathway. The last trend that I'll bore you with, I promise, it's all for a good cause, is the atomic radius, or half the distance between the nuclei of two atoms. So atomic radius goes the other way. Oh, sorry. No, it goes this way. That's silly. So it kind of makes sense that it increases down because the number of electron shells increases. There's also metallic character. Okay, anything on this sort of trajectory is going to be metal. Anything on the other side of that line is going to be a non-metal. Yeah, that's pretty much everything for that. So when we have an element, we know, as I went through before, We have our nucleus, got protons, neutrons, and then we have 7. It's not even close to being straight. Each of these shells, you have an increasing level of energy as you go outside the shell. Positive charge within the nucleus attracts the electrons, so they stay tightly bound. The further out the electron is, the more likely it is to either be stolen or another one comes in and is added to it. The entire periodic table is based on the electron configuration. So in the electron configuration, we have the shell, so 1. Then we also have the suborbital. Because if we have, there's 118 elements on the periodic table. And there's only supposed to be 8 in each one. 8, 16, 24, 32, 40, 56. That doesn't work. So in these orbitals, there is S and D. They're like 3 different lanes on a highway. And if we look at the first shell, it only has an S orbital. So it just has 1 lane inside of it. It can have 2 electrons traveling in different directions inside that subshell. So now this is helium. Again, we'll go into this in more detail. But the entire periodic table is based around the filling of these shells. Okay. Does that make sense to everybody? Not just speaking gibberish. Okay. Let's do, again, this was meant to be a sort of intro to the periodic table and what it all means. So I'll go a little bit further. So again, we know that the electron configuration of the atom tells us everything about the bond. If there is only 1 valence electron in the outer shell, it's not going to try and gain another 7. So this is lithium, Li, chlorine, over here, group 7. It's not going to try and gain 7 more electrons. Sorry, lose 7 electrons. Because energetically it doesn't make sense. Groups. I feel like I'm repeating myself over here. 1, 2, and 3 form cations. 5, 6, and 7 anions. All right, I think I might leave it there because that's pretty much the entirety of topic 1. What are we thinking? Do we want me to work off materials or happy for me to work out of my head? What's the consensus? I don't mind either way. Anyone else? So we're going to finish there this week. Get into it next week. I don't mind. I pretty much just